Hello everyone, in this tutorial I'm going to show you how to simulate a composite beam in Abacus software. As you can see in this example, we have two I-beams and they're on the top of each other, and in this example I'm going to use a steel and copper. These are just examples. This might not happen in real life to combine a steel and copper, but just for sake of example to show you how we can create these type of composite beam in Abacus. So what we have, a beam with a length of 5,000, which is pinned on one side, and the other side we apply 8,000 Newton in y direction, and we have steel and copper. The bottom beam is made out of steel and the top one is made out of copper, and these are our dimensions. So before starting the Abacus software, I want to show you the hand calculation. So we want to find some parameters such as maximum deformation, maximum bending moment, and maximum bending stress. So when we find these values in Abacus, then we can compare them with our hand calculation. Okay, so the first thing we have to do is to find the moment of inertia, and we can do that by using a formula. And as you know, these are all coming from the first year of engineering at university, so I hope that you know all these formula, and if you don't know that, you can simply just Google and look for a moment of inertia for I-beam and read about those, because the aim of these tutorials are just a software, and I'm gonna quickly go through the hand calculation and analytical section. So this is a formula that we basically use when the neutral axis is not in the middle for the geometry. So the neutral axis is located here at 150 millimeter, and so what we're gonna do, we're gonna find the moment of inertia for three sections. So this section is for the top part, this one for the middle, and the last part is for here. And as you can see, in the last part we don't have the second part. And why? Because the neutral axis is located exactly in the middle, so we don't have to do the second part. We only do a second part when the neutral axis is not located in the middle of our geometry, so we have to compensate for that using this top formula. So so using this formula, we found a moment of inertia which equals to 4.4 times 10 power 7. The next step is to calculate a moment of composite, and the formula is 1 over EC equals to the portion of steel divided by Young modulus of steel plus portion of copper divided by Young modulus copper. So here currently we have 50-50, so 50%, and based on that we can find the modulus of composite. So this is when I say composite, it doesn't necessarily mean a carbon fiber. So composite, anything that is made out of two different materials, we call it composite in engineering. But I know that when you say composite, you're always thinking about a carbon fiber, but that's not the case. And what we have here, also we have a maximum deformation that can be calculated with the following formula, and here we have the displacement equals to 50.5 millimeter, and then we have a maximum bending moment which equals to a force times length of the beam, and this is a value for the maximum bending. And finally we have a bending stress formula which equals to m times neutral axis divided by moment of inertia, and bending stress equals to 153.4 megapascal. So these are our hand calculation, and we are more interested in to compare the formation. So now let's go to Abacus and see how we can simulate that in Abacus software. Right, so in order to make this composite beam, there are different ways of doing that. And one way is to make your model as a single part, as I have done here. So if you look at this one, you'll see that I made this sketch in Abacus in a single part, and I created a partition using a datum plane. So now I have a two separate part, top and bottom, and then based on that I applied properties. So to the bottom one I applied the steel, and to the top part I applied copper. The second way is basically to use to create a one part like this, just a single item, and then copy that one and create another copy, rename it as a copper, and in assembly you can assemble these. And what I have done in the interaction section, I defined a tie constraint between them. So it doesn't really matter which method you are using. I'm going to show you the result. So if I go to V1, which I used one single, so you look at this, the stress, one meter stress 1.55 or 155 megapascal, and the displacement is 54.31 millimeter. Now let's check the result in the for a second example, and you will see that the stress very close, 156. The previous one was 155, so very close, and the displacement is 54 again, 0.59. So it doesn't really matter which method you choose. The result at the end that you get is gonna be similar. And this is the case generally with the FEA software. So you don't generally have the one correct way of doing something in a finite element software. There are different ways of doing it, and it really depends which one you are more comfortable with. And also sometimes one method is better than the other because you can quickly modify it. But in general, as I said before, there are different ways of simulating something, and it doesn't necessarily, it's not a way that you say, okay, there is only one way of doing something. Okay, so for this example, I'm gonna go for the first example because we haven't had this type of geometry in this course, so I'll use the first one. So let's create a new model, and I'm going to call this one composite beam. And so double click on the composite beam and go to part section, and then what I'm going to do, I'm going to create a part, call it composite. It's going to be 3D deformable solid, an approximate size, let's make it 300. Click on continue, and first of all I'm going to create a construction lines here in the middle, and I'm going to fix this one. Then I'm going to draw half of the beam, so using this one, so go up here, like this. And when you give a dimension, make sure you always give a smaller dimension first and then the large one. So this one is 10 millimeter, and this one again is 10 millimeter. So from here to here I know that this is 35, and from here to here is 150. So now I can move this one to the middle. So let's just create a construction line in the middle section. I'm going to zoom in, create another one here, and I'm going to fix this one, click on OK, and then I'm going to use coincidence and move this line to here, and then we can use the mirror from here, and it will ask us select the type of the mirror, so it's going to be copy, select this one, and then we'll select everything that we want to basically mirror. This one, and this one to mirror to the other side. Click on OK, and then we want to also mirror this one to the bottom because we have two of these. Okay, so I missed selecting this one, so I'll just do it manually. And then also I can get rid of this line, but before doing that I will just use again mirror command one more time, and click on copy. This time select this one, and again select everything. In order to select everything, you can hold shift and select all the lines. We don't want the line at the bottom. Click on OK and click on done. So now we are done with this one, and what I need to do, I just need to get rid of this line that I created, otherwise we cannot create extrude. So if all the geometry is closed, and if I cancel everything, I should be able to extrude this one. Yeah, so now I should give a depth of the beam, which is going to be 5000 millimeter. Click on OK, and that's going to be our beam. So our current beam is a one piece, and because I have two different material, it's not possible for me to give these two different material. In order to solve this issue, what we need to do, we need to create a partition. So we have a beam 1 and beam 2, and we can do that by creating a datum plane from the face. So either you can select the top or bottom surface. I'm going to go for a top one, enter a value, and just check the direction. So currently it's going up. I'm going to click on flip, click on OK, and so I know that from the top to middle is 150, and then I can create a partition using a datum plane, this one, create partition, and as you can see now I have one at the top, one at the bottom. Okay, so next step is to create a property. So create one, so click on create material, call this one still, mechanical elasticity elastic, that's going to be 2e5 or 2 times 10 power 5, and Poisson ratio 0.3. click on OK, create a section for this, call this one still homogeneous, continue, and assign this one to the bottom one. Click on OK, and then I'll do the same for the top one. Create a material, call this one copper, mechanical elasticity elastic, and for young modulus times 1.2 e5, Poisson ratio 0.34. click on OK, and again create a section for this one, call it copper, continue, select the copper, OK, and assign this one to the top section. Click on done and select the copper. So now we are done with this section, and we go to assembly, import this one, click on OK. We only have one assembly, so we don't have to do anything here. Step, we create a step for this one, static general. We can turn this nonlinear on, minimum 0.1, initial 0.1, and minimum 1 times 10 power minus 15, and this one 1000. Click on OK, and then interaction. So in interaction, what we can do, we need to create a coupling because we're gonna apply a load to the face. We can also apply load to the edge or this point here, but it's better to apply to the face here. So what I'm gonna do, I'm gonna offset this point, the middle one, in a minus z direction. So it's going to be 0, 0, minus 20, and create a reference point here and use a coupling. Select this point and node region, select this one, hold the shift and select the top one, click on OK. So we created a coupling, so anything that happened to this node will happen to that surface. So now I can go to load and create a concentrated force there. Click on this node, click on OK, make the first one 0, 0 and this one minus 8000. Click on OK, and then I'm gonna use the pin. So I'm gonna use the first one again, select this face, and pin this one. So now I am done with the load as well. Next step is a mesh, and in parts, as you can see, the color is yellow, so that's the sweep mesh. Is good, and I'm just gonna need to apply a size for this one, and let's try 50. I think 50 is okay, especially if you're using the educational version. You can go a little bit higher than this, so you don't pass the limit. But I think I'm happy with 50. So apply this one, click on OK, and assign a mesh. Yes. So this is not a fine mesh, but it's good enough to give us some results, quick result. But if you want a more accurate result, it's better to reduce the mesh size to 15 to 20. Okay, so now I'm going to create a job that's going to be composite beam, card number 2. And I'm gonna submit this one. If I've done everything correctly, I shouldn't get any error. We'll see. Okay, so no error, and let's wait for a soft result. Okay, as you can see, that was a very quick simulation after 6 increment was done. So if I go to result section and plot the result, and then if we go to displacement, that's 4.66. So as you can see here, the result is a little bit lower than what I have found in the previous simulation. So it's clear that I have made a mistake somewhere. So and this is not a problem as long as you know where to look for the problem. The first thing you always have to check if your numerical result is not similar to the experimental is the material property. So you have to double check if what you have put there is the correct unit system and the values are correct. So currently this is, yeah, that's 1.2 times 10 power 5. So this one is correct, and I'm gonna check this one. This one is correct too. So there is no problem here in the property section. So the next step to check is the basically the geometry, and again the same thing, you have to check if your unit system is correct. So what I'm going to do, I'm going to check this one. So the unit system definitely is correct because I'm using millimeter. I'm going to just check the dimension. So this is 35 is correct, this is 10, this is 150 is correct. And okay, so I found a problem. So the problem is here that I didn't give a dimension to this one. So I'll just add a dimension from here to here. Instead of 5, that should be 4. Because if I show you the what we had here, so that was 8 millimeter, and what we had in the geometry was 10 millimeter. Okay, so I'm gonna check that for the bottom one as well if it's correct. Yeah, so I'm gonna cancel a dimension, so that's 4. Click on OK. Done. So when you do any modification, the first thing you have to do is to regenerate. So as you can see, there is a yellow text here. That means that what you have applied there, the modification you have done there, is not applied yet. So what you need to do, you need to right click, regenerate, so you apply those modifications. The next step that you have to go to mesh, and you have to create a mesh again. And this is simply because when you change the geometry, then the mesh is not valid anymore, so you have to apply a mesh again. And when you apply a mesh for a modified geometry, generally it's going to be quick because it's already applied, so we haven't done a big modification. So I'm going to just select everything again and make sure that this is 50, and again assign a mesh, yes, and then we can right click on this one, submit a job, click on OK. Okay, the job is done, and if I select the results, and if I go to displacement, as you can see the displacement is 50.45, and if I compare this with what we have got there, so as you can see the result is 50.5, so this is very close to the new to analytical result. So the displacement that we got from the numerical, the error is very small, so this is 50.45, and the analytical result is 50.5. Okay, so now let's see the stress in the our beam. So bone pieces stress is 146 megapascal, and if you look at the stress, it's clear that this stress is caused by bending. So when you apply the force and here, and as you can see the maximum stress is located around this area, which is 146, and this is quite close to what we have got as a stress as well. It's 153.4 megapascal. It's a good practice if we actually change the mesh size and see that if the stress result is going to change. So generally the smaller mesh, the better results. So we'll see that if this will actually gonna change our results. So now let's basically reduce this mesh size to maybe 25, apply a mesh and assign a mesh, slightly better, but it's not, so I'm just gonna go for much smaller, let's say 15, and assign this mesh, and let's apply run this simulation again. This time should take longer to run this one, but we'll see that if that affected the result. So there is a section in this tutorial about mesh study in a improver example section. Please watch that one, and it has a lot of useful information that how you need to do a mesh study to find the appropriate mesh size for your model. Okay, the simulation is done. Let's just see the result. So as you can see, the stress changes slightly. I think it's 148 right now, and I'm sure that if we make our mesh smaller than this, we would be closer to the value that we found here is 153. It still is close enough. So here is 148 and here is 153, and I would call this one appropriate error. So it's not really a big error, but I'm sure that if you reduce a mesh more and apply a finer mesh, you would be able to get a much closer result to the hand calculation. Okay, I hope you enjoyed this tutorial. So in this tutorial you learn how to create a composite beam and how to basically compare your analytical result with a numerical result. I hope you enjoyed this tutorial. I hope to see you in the next video. Thank you so much for watching.